Hey everyone, and welcome to another Explainer. Today we're taking a seriously fascinating journey from simple movement all the way to complete mathematical mastery. You know, we often think of math as just, well, static numbers sitting on a page. But today's topic? It's quite literally the fundamental language of motion and direction. We are talking about vectors. Whether you're mapping a flight path, programming how a character jumps in a video game, or just trying to understand how shapes move through space, vectors are the invisible arrows making the whole shebang happen. Let's get started. All right, let's dive into this. Here's our game plan. We'll start with vector basics, jump into math operations, calculate vector magnitude, map out position vectors, and finally, we'll master vector geometry. Starting off with Section 1, Understanding Vector Basics. So to really wrap our heads around vectors, we first need to talk about translations. Now, in geometry, a translation is just a very specific type of transformation. It's basically when you move an object in a given direction for a specific distance. The key thing to remember here is that the shape doesn't rotate and it doesn't get bigger or smaller. Every single point on that object moves the exact same distance and in the exact same direction. It essentially just slides right across the grid. Okay, so how do we actually describe that slide? Well, that brings us to a massive distinction in math and physics, the difference between a vector and a scalar. Now, a scalar is probably what you're most used to working with, right? It's a quantity that only has a magnitude or a size. Think of things like temperature or speed. It's literally just a number. But a vector has both magnitude and direction. It doesn't just tell you how far to go. It tells you exactly which way to head. And this brilliantly illustrates what we call a column vector. It kind of looks like a fraction trapped inside some tall brackets, but trust me, it's not. The top number dictates your horizontal movement, the x direction. A positive number means you move right, and a negative means you move left. The bottom number dictates your vertical movement, the y direction. Positive is up, negative is down. So if we look at the translation vector 3 over negative 2, it's telling you precisely to slide 3 units to the right and 2 units down. It's basically a perfect set of driving directions.
Moving right along to Section 2, Vector Math Operations.
You know, vector addition is actually beautifully simple. If you start at an original coordinate point, let's say x is 1 and y is 2, and you apply a translation vector of 3 over 2, you simply add the components together. You add the top x values, so 1 plus 3 gives you a new x of 4. Then you add the bottom y values. 2 plus 2 gives you a new y of 4. So your new coordinate is 4, 4. The exact same logic applies to the next example. If you start at 2, 3, and add a vector of 4 over 1, you land precisely at 6, 4. It's just a completely predictable step-by-step mapping system.
All right, so we know we can add vectors to points, and we can add vectors to other vectors. But let me challenge your intuition for a second. We know scalars are just regular numbers without any direction. So, what do you think happens when we multiply a directional vector by a negative scalar? Any guesses?
Now, what's really interesting here is how scalar multiplication visually answers that exact question. If you take a vector A and multiply it by a positive scalar, let's say 3, it just stretches the vector out to be 3 times as long in the exact same direction. But if you multiply it by a negative scalar, no way. It reverses the direction entirely. It literally flips the arrow around. Now, to add vector A to vector B, you just place them head to tail. You walk along vector A, and from where you end up, you just keep walking right along vector B. The direct, straight-line path from your very first starting point to your final destination, that's your new combined vector, A plus B.
Let's hit Section 3, Calculating Vector Magnitude.
Finding the magnitude, which you'll often see written with these vertical bars on either side of the vector name, it might sound a bit intimidating, but I promise you, you already have the tools to do this. The steps are super straightforward. First, identify your x and y values from your column vector. Second, square the x value. Third, square the y value. And finally, just add those two squares together and find the square root of the total. Does that sequence of squaring and square rooting sound familiar to anyone? Because it absolutely should.
Yep, calculating magnitude is quite literally just applying Pythagoras' theorem. When a vector moves a certain distance right and a certain distance up, it creates this perfectly right-angled triangle where the vector itself acts as the hypotenuse. Your x movement is the base, and your y movement is the height. So the magnitude is simply the square root of x squared plus y squared. It's this incredibly elegant bridge between algebra and classic geometry.
Section 4, Mapping Position Vectors. So position vectors are kind of like an anchor. A position vector is a very specific class of vector that always originates from the origin point, coordinate 0, 0, which we label as O. So when you see a vector denoted as OA with a little arrow over it, it explicitly means the vector starting right at the origin O and traveling directly to point A. It functions exactly like a set address. Position vector OA essentially just gives you the literal coordinates of point A relative to the absolute center of your graph.
And finally, the boss level. Section 5, Mastering Vector Geometry.
Let's see how all this builds up when we look at a shape, like a triangle. In vector geometry, there's often a bunch of different routes you can take to get from one point to another. But here's the cool part. Whichever valid route you choose, adding the column vectors will give you the exact same result. For instance, to get from point A to point C, you could just take the direct vector AC, which is named Q. Or you can travel from A to B along vector P, and then go from B to C. Because vector addition is commutative, A plus B is the exact same as B plus A. This rule, combined with what we learned about scalar multiplication, allows us to find these complex alternative routes and express any line segment in terms of known vectors, like P and Q.
So, the absolutely crucial point here is how we use these alternative routes to prove geometric relationships. This is golden for your exams. If you can use algebra to show that vector AB is equal to some scalar number k multiplied by vector CD, boom, you have mathematically proven that those two lines are perfectly parallel and that AB is k times longer than CD. Even more powerfully, if you can prove that vector AB is equal to k times vector AC, well, think about it. Since they share the common point A and they are parallel, they must be part of the exact same straight line. We call this being collinear. These right here are your golden rules for completely dismantling high-level geometry problems. And that brings us to the end of our explainer. We've gone from looking at a simple set of column numbers to actually proving the structural layout of geometric space. But before you go, I want to leave you with this thought to chew on. If vector geometry allows us to map and prove literally any movement in space using just simple triangles, addition, and scalars, what kind of complex real-world structures could you decode right now? Think about the massive bridges you drive across, the orbital trajectory of a satellite, or even the physics engine running your favorite video game. It's all just vectors. Thanks so much for hanging out with me today. Keep looking at the world through that mathematical lens, and I'll catch you in the next one.